what we want to talk about today is some of the roadblocks that are getting in front of people from being able to lift and shift and get their applications out there. And so we're from Elastifile, or I'm from Elastifile, and we've been working with Google closely to make this a little easier, this journey. We built out a high-performance POSIX file system, distributed file system that deploys super easy inside of Google Cloud to kind of shorten the distance between application on-prem to running in cloud and take advantage of the resources out there, okay? So that's kind of the idea. You know, once you open up the Google Cloud Console and get a feel for what's there, it's pretty amazing. Click of a button and I can deploy a machine, 10 machines, thousands of machines, and have access to a seemingly unlimited set of resources at my fingertips. You know, the latest Skylake CPUs and GPUs from NVIDIA, and you know, API-driven applications like ML and AI, all at your fingertips and all ready to go. So what I want to talk about today is what stands between us and getting our applications out there. So a couple of things that stand in the way for traditional applications to go run in cloud. The nice thing about Google is they've developed a lot of new ways to do computing. You know, object-based storage, for example, and containers and all of this. But the problems we have is a lot of our applications are compatible, right? So for example, there's a lot of data sets that require POSIX file systems, right? POSIX, familiar term in this crowd? Yeah, everyone's shaking their head. Yeah, so POSIX is a lot different than object, right? POSIX has, you know, certain rules, there's file metadata, file hierarchies, and a lot of our applications are built to expect a POSIX file system. They do fopen and not GCS opens, right? They don't understand object stores, which is a way to store data, but it's completely different. So natively, the only POSIX you can get in cloud is inside of VMs, but there's no shared file systems that are POSIX compliant that can really scale, right? So beyond that, it's the other big challenge is kind of the data gravity problem. I have big sets of data that live on-prem, and I need to get that data close to CPUs to do my analytical work. How do I do that? How do I bridge the gap in a way that's reasonable, since, you know, we're traveling over long distances with high latencies? Also, when you're moving POSIX data to cloud, if you've ever done like a GSUDL to upload your data into GCS, you know, sometimes you get surprised. You go look at the file and it's kind of been stripped of a lot of metadata. Any file hierarchy that exists, it's kind of disappeared, right? So those things kind of get in the way of a lot of applications. And then lastly, it's the perception is it's really expensive to run file system type workloads in cloud, right? Do people concur with that? You know, there's not a lot of native services there, so it's a lot of do it yourself and build your own, which is kind of antithetical to the whole cloud idea, which is point, click, go, do my work and get out, right? I don't spend time in infrastructure. So what we set out to do is solve these problems to a large extent, you know, so you can get to more science and computing and getting your job done instead of, you know, spending time messing around with pipes and disks and servers and the like, okay? So let me talk a little bit about Elastifile. What we built is a highly performant POSIX file system. It's a shared file system. Looks like NFS, but scales like GPFS and Lustre, if you will. But we did it in a way that's really simple, easy to scale, at a price point you can actually afford and get moving into production fast, okay? So what I want to talk about is, you know, this isn't we're not the first company to invent NFS file system and the like, but in order to do it right and do it in cloud, there's a kind of a puzzle that you have to solve for, and there's several pieces that have to come into play, and in our opinion, in order to make it work in a way that's not only technically feasible, but commercially feasible and the like. So in cloud file alone, you know, to play the game, you have to be able to, you know, do POSIX and file and all of that. I'll speak about some of those details, but that's not it. You know, I can stand up a, you know, GPFS, for example, in Google Cloud, but it's a lot of work. You have to be an expert. There's a lot of provisioning. You know, things aren't fully supported. So the first thing you have to do is make it easy, right? And cloud is synonymous with easy, meaning click button and it works and goes. All right, so that's requirement number one. Number two, it has to perform, right? It has to be able to handle the workloads that you're throwing at it without hitting that proverbial cliff and falling off and leaving you stranded, right? And lastly, we have to perform not only with the first machine, but a machine 10, 100, 1,000, 10,000 and beyond, right? It has to scale deterministically and reliably. And then lastly, you know, the costing has to make sense, right? It has to be at a price point that's competitive with other options, you know, so your boss will sign off on it. So let me show you what we did to meet every one of those objectives in our current offering we have with Google. Firstly, you know, to be in cloud file, there's a few things we have to check the box on. One is we have to be POSIX compliant. For example, there's not POSIX compliance in object stores. Object stores are eventually consistent. And so if I'm a POSIX file system, when I write a piece of data, and I'm a database that wants to read that data, I have to be guaranteed that the last piece of data written is the next one that I read. And if my data is eventually consistent, if I read the data and I get a stale piece of information, that's bad, right? That creates corruption and problems, and our applications don't know how to handle that to a large extent. And I don't know about you, but who has the time to go back and rewrite all the applications that your researchers and students and the like are using? You know, you don't have source code in MATLAB, right? And it's just not really feasible, right? There's a whole bunch of applications, hundreds or thousands, that need this kind of compliance. Second thing is, you know, we designed this to use any native NFS client. The kernel level NFS, no special drivers needed, no special client needed, so extremely accessible. You know, spin up any VM in cloud and we can connect to it and go. Thirdly, you know, a distributed parallel file system. File systems are great, but when I have parallel applications that send hundreds or thousands of connections at a single time, I have to be able to handle that. And then enterprise features. So one thing we did is spend a lot of time not just building a great file system, but one that works, you know, with the enterprise in mind. So features like snapshots, asynchronous replication site to site, compression and deduplication built in, high availability, and then this idea of checking in and checking out data. Let your data be in the medium that makes sense for you, whether that's cloud storage, you know, active in the file system, or maybe parked away in your private data center somewhere. Okay, and then protocols. So there's a lot of approaches to doing files. Sometimes it requires installing you know, file system drivers and like. To a large extent, we don't really want to be in that business. We're in the business of trying to access as much of the kind of common data as possible. NFS and SMB or common protocols are available, so we make them fully compliant, ready to use with any application. Okay. So let me switch into, I'm going to introduce my friend Andrew here. We're going to show you a couple demos as we go to build this. Okay, we're going to do this on demand. So what you're seeing here is an HPC environment appropriate for the show that we're at. And so we're going to stand up first the storage component, which is an Elastifile cluster in Google Cloud, and then we'll come back a little bit later and we'll stand up using Elastic Cluster Slurm and some nodes and get to the point where we can actually start running some HPC applications. Okay. So these are some of the components that we're using. Question?
How many VMs do you need to build a small cluster to set up?
Good question. So the question is, how many VMs do you need to start a cluster? We start with 3. So the model for us for high availability is we do replication of data. So replication factor 2 means we can lose a node and continue to operate at full speed. So we start with a minimum of 3 and then scale to pretty much whatever you need. You know, dozens, hundreds, and the like. And so each cluster is going to have a certain amount of capacity in it. And you can choose whether that capacity lives on persistent disk, HDDs, persistent SSDs, or even local SSDs, which are rocket fast. They don't have as much redundancy as the PDs, but we overcome some of that with our own resiliency there. So next one is performance in our puzzle pieces. Just a little bit about performance. We're really optimized as a file system for really high I/O and low latency patterns. Kind of our claim to fame is we can scale linearly and keep latency at like millisecond or sub-millisecond speeds. And so it does really well. You need a lot of IOPS, really low latency. But on top of that, we've designed this to have a pretty broad performance band, leveraging things like distributed file system, distributed metadata, flash. We have a system where we don't cache data at all. So you can't cheat. You can get really good performance at small scale, but fall off a cliff later. You know, the performance will get low, tends to be consistent with high. So we're really good for transactional workloads, small blocks, tons of small files, hundreds, millions. We run containers really well, VMs really well, databases, in addition to any sort of file type workloads. And then throughput workloads work really well also. Since we're linear in scale, we can pretty much push line speed of the VMs that are hosting us. So when you get into gigabit, multi-gigabit throughput needs, we can do really well. Where we tend to start to peak is about block sizes of about 256K. We're not really well optimized for really large block type solutions like maybe dumping MPI data that Lustre does really well. That's not really our space. We're more about the NFS oriented applications, which to a large extent is a lot of what happens in kind of this high performance environment as well. Okay. Here's an example. We did a head-to-head with another popular file system, Lustre, Now the cluster's NFS server. And so kind of breaking this down, we have 3 different tests here. One's an I/O test with small blocks, 4K, the kind of stuff you'd see with VMs and databases and small files and the like. So there's a read test, or run a full read, full write, and a kind of mixed workload test, 70-30 read-write. So just drawing your attention to it, what you'll see with us is nice linear scale. As we add more nodes from 4 to 16 to 32, our line goes up nice and straight in all these different tests, right? And it's frankly a steeper angle than the other guy. Over here you've got more of a throughput test with larger blocks. Same thing, we've got nice scalable reads, nice scalable writes, and nice mixed workload as well. And then you get the much larger and kind of the consistently the same. You'll see the scale, this one's kind of measuring I/O, so we're going from tens of thousands to almost a couple million I/Os up here. I mean, that's a lot of transactions that are going through on a relatively small cluster. And by the way, this is a cloud-based cluster running on persistent disk. And then over here, you're looking at throughput, right? So we're pushing 10 to 20 gigabytes per second of throughput. Same thing down here. So we can kind of optimize for the workload that you're looking for, okay? All right, scale. Can I do that at scale is the big question, and especially in this environment where people push the edges to the extreme. So we designed this to be a distributed parallel file system. Like I said, the share nothing, write anywhere architecture, so every node is active. Anywhere you enter the file system, you can get to any data. We did a lot of work, designing a new way to distribute metadata. We have no centralized metadata database, so there's no choke point there. So any system can own any piece of metadata across the entire cluster, and the nodes communicate with each other to figure out who owns what metadata, and if something happens, a node goes down or whatever else, ownership is dynamically moved, even in the middle of an I/O. It's highly responsive. We designed a new consensus algorithm to handle transactional workloads, and you kind of decide who's the winner in the event of a problem. So we're designed for failure, we expect it, and we optimize around it. Lastly, that gives us the ability to be deterministic as demand grows, right? So I demonstrated that on the last one. Also, while we're operating, the ability to dynamically add and remove nodes without a lot of work. In Google Cloud, you click a button and another node shows up and performance just gets that much faster, okay? All right, so I want to show you an example of what that looks like. So what I'll show you here, this is a demo that we set up. This one was a little easy to record. So we've got a 30-node Elastifile cluster running in GCP. We spun up a whole bunch of containers, and then we're running a parallel file system workload on it to generate a lot of I/O and a lot of traffic. Okay. So you'll see in here, this is OpenShift running in Google Cloud. We created a whole bunch of, we got 100 client nodes in here, Elastifile running, and then each of the nodes has 10 containers on it. So we're going to start systematically adding more and more demand, compute or I/O demand against us. Those are all some fancy image of a bunch of containers running together. Okay, so we started out with 250 containers, each made 10 NFS connections back to our file system and started running this 70-30 read-write workload. And so as kind of a baseline, you see we're pushing almost a gigabyte per second. Latency was about right around the 1 millisecond range. Okay, we double it, we go up to 500, and you'll see these graphs start to go up and to the right, right? Now we're up to 1.5 gigabytes per second, so we doubled there, I/O's going double. But if you notice, it's going quickly, but the millisecond stays right in the same range, right? Response time is nice and consistent. So we'll go bigger, 2.3 gig, milliseconds are still low, I/O's doubled as well. We're starting to get the pattern, right? Now we're up to 10,000 concurrent NFS connections, and the system is handling it like a champ, okay? Same thing, 1.3 milliseconds, we're putting 3 gigabytes per second, and this is transactional I/O that's happening here. Right, if we kick that to full read, try to do a lot of, data loading and the like, our throughput will go even higher. Okay? Questions on that? Make sense? All right.